Good morning, everyone. First, I'd like to thank OMICS Group for inviting me to be a part of this conference. Is this loud enough? Can you hear me? Okay, the previous speaker have given you a very good suggestion, so I believe we will get to know each other better in the next several days and learn a lot from each other. My talk today would be on the dry and removal modeling areas. Some materials might be too technical, so I try to omit some details. Okay, first, I'd like to give you some background knowledge on this topic because we all come from different background. We have different expertise. So for air quality study, the typical cycle of a pollutant would be, the first emission from sources like the industry, the natural industry, the traffic, from agricultural and natural resources. That's the emission. Once the pollutants are emitted into the atmosphere, then they would undergo transportation, diffusion, so the pollutants can be transported from this area to another area. Then they can convert to different pollutants can be converted to different chemical species. It's called chemical transformation. And pollutants can be removed from the atmosphere. This process are called dry and wet deposition. Okay, dry deposition. So when pollutants are transported from the atmosphere onto the lower layer of the atmosphere and contact the Earth's surface and uptaken by all different surfaces such as canopy, soil and water, these processes are called dry deposition. And inside, in the atmosphere, if the pollutants are first incorporated into hydrometers such as rain, cloud droplets, rain droplets, or snow particles, and then delivered to the Earth's surface, this process is called wet deposition. By the way, the fog deposition is also one type of wet deposition because fog is just one type of cloud touching ground. So why we need to worry about the deposition? As I just mentioned, the dry and wet deposition are important, are the only removal mechanism for pollutants. So for air quality forecast, if you want to know the pollution level in the air, you have to quantify this removal mechanism in order to forecast the air pollution. Also, in order to assess the effects of pollutants into different ecosystems, you have to know their input to the ecosystems. So we need to quantify the dry deposition amount. As I just mentioned, for the dry deposition, the pollutants have to be first transported to Earth's surface. So, and then contact when it passes a very thin layer above the canopy, then it can be collected by the canopy or collected by the other surface. So in the modeling approach, we consider this as three different steps, like the aerodynamic process, called Leiming layer, and the uptake layer. For the wet deposition, this is the following job. So pollutants can be collected by this job and then delivered to the surface. A simple comparison of dry and wet. For dry deposition, as I mentioned, in theory, it's very complex because it involves too many chemical and physical processes, and many processes are not well understood. So because it's so many unknown areas, so technically we treat it as a very simple process, using a very simple scheme to deal with this process. For wet deposition, the theory is very simple. the pollutants just incorporated into hydrometers, then falling on the ground. However, because the falling droplets have a very complex dynamic process, so its treatment is very complex. One thing I'd like to point out is that dry deposition happens all the time, even during the rain process. In some literature, some authors are frequently mistaken this concept. So in chemical transport models, these two processes are basically parameterized because you can't use a very detailed mathematical formula to deal with. So I'm going to split into these topics like particle dry deposition, gas dry deposition, and particle scavenging by rain, by snow, and gas scavenging by rain, by snow. I should mention first that pollutants can exist in both particulate matter and in gaseous form. Because I don't have too much time, so I don't want to go too much details. But briefly, for particle dry deposition, the earlier measurement for particle deposition were made mostly within the chambers or tunnels, and the later measurements after 1990s were mostly conducted in the field, and we found that the later measurements identified the particle deposition were higher than it should be, than it was thought based on the chamber measurements. So because with the increase of the computer power, currently the chemical transport models can have a size-resolved aerosols. So then there are quite a few size-resolved particle depth EMEP model developed, at least a few of these. And also a few review papers were published on this topic. The theory, the approach for dealing with the particle deposition is use a resistance analogy, which means the deposition velocity is a reverse of the resistance. This one aerodynamic resistance, this one surface resistance, and plus the gravitational setting velocity. I'm not going to details of the theory. Just want to point out that recently we have developed, we further extended our size-resolved particle dry deposition into a bulk one, because in many monitoring networks, only the bulk mass is monitored. So in order to quickly estimate the dry deposition, a bulk particle density model is needed. So if you have interest, you can look at this publication. For gas dry deposition, again, like we also use the resistance approach. The deposition velocity is a parameter that's used for describing the dry deposition of gaseous pollutants. It is parameterized as the reverse of the total resistance, including the aerodynamic, quasi-laminar, and the canopy resistance. And there are two major pathways for gaseous pollutant. One is the stomatal uptake. The leaf has a stomata. The gas pollutants can be diffused into the stomata. The other one is non-stomatal uptake, by the leaf cuticle or by the soil. That's the basic concept. For the non-stomatal resistance, the earlier models were very simple. They use just a simple, use an empirical constant for different land use category. Later models include more parameters such as the leaf rate index, or use also like a model we published in 2003, also consider the frequency velocity, relative humidity, and so on, and canopy wetness. For some particular gas species such as ammonia, some models also have different parameterization considering relative humidity or Hern's law constant. For stomatal uptake, again, the earlier model, which is one of the most widely used model by Wesely, the stomatal uptake was only considered as a function of temperature and solar radiation. But there are other approaches in different chemical transfer models. Some models, like the CMAQ, US EPA chemical transfer model CMAQ, use the Jarvis type model. And the Canadian air coating model, ORAMS, use the 2B leaf model, which means we treat the whole canopy as sunlit and sunset fraction. And some models even consider the CO2 effect. So I am not going to details on that. The recent progress in the community include developing the bidirectional approach for ammonia and for mercury, and some ozone flux model for agricultural canopies. And some model started making use of remote sensing data such as leaf index and so on. There are a few model intercomparison studies showing large uncertainty still exists in commonly used models. The recommendations I can give on the dry deposition is that I think many air quality models need some updates because there are more and better and improved deposition scheme available, but many models are still use the very old version. And if where possible, I suggest to use the more detailed input data such as leaf index, roughness length, because these data start being available at a grid level, such as at a very high resolution level, such as 1 kilometer resolution. And although there are a few ammonia bidirectional model and mercury and bidirectional model available, but no model intercomparison have been done yet. So this should be done to look at the difference between the models. And for toxic compounds, pesticides, there are actually no general scheme available in the literature. For particle scavenging, that's for dry deposition. For wet deposition, for particle scavenging by rain, if you want a very detailed description, you have to know the size distribution of the raindrops and the particle size distribution. So that's very time consuming. That's called the explicit coagulation theory. So only one model currently uses that approach. Most models would use the scavenging coefficient approach. Scavenging coefficient is defined as the first order time change of the first order of the concentration change with time. One model have a microphysics model which couples cloud microphysics with aqueous phase chemistry, but it's only deal with a few most commonly studied species such as sulfate, ammonium, and nitrate. For particle scavenging, some models don't even bother to consider that. Again, that's only one model using the explicit coagulation theory, but most models would be used the scavenging coefficient. Okay, similar. One recent development is a project that I've been leading in my department. We systematically reviewed and assessed the uncertainty of the scavenging coefficient for particles scavenged by both rain and snow. We have 2 review papers, this one 2010 and 2012. We also have one paper conducting sensitivity studies. And then based on those results, we developed a new parameterization published in Geoscientific Model Development just a few months ago. And we further extended this size result model into the bulk version, and this one paper is under revision. From the first 3 studies, we made the recommendations that the empirical formula. In some schemes are simply generated from the field data. Those are called the empirical formula. We think that those empirical formula should not be used in CTMs because it considers all the processes that contribute to the scavenging process. And some processes are already considered in chemical transfer models separately, so you can't double counting those processes. And we recommend that the upper range value of the theoretical formula should be used because they are still very lower, much lower than the field measurements, and they are close to the reality. and we think we can develop a simple one. I'm not going to describe the process, but anyway, we use an ensemble of all the available formulas for all the input parameters, and we run it for a large range of precipitation intensity. This is scavenging coefficient as a function of precipitation intensity, and each line represents one aerosol size. Okay, so these 6 lines are examples of these hundreds of lines. We found that this formula can perfectly fit into a log linear relationship or a power law relationship. Then we find the interception of each line and the linear and the slope. Then we parameterize those slope and slope and interception, which are 2 parameters A and B as a function of particle size. So these are the final products. We extended it into bulk scheme, so you only need 2 parameters and B. You don't need a formula. For gas scavenging, there's very limited knowledge on this. Again, scavenging coefficient is one commonly used approach, and some use Harris law equilibrium, which means you assume the gases concentration in equilibrium within the air and inside the water, inside the droplets. And some use mass transfer approach, which is this is a kinetic approach, which is you do not make any equilibrium assumption. So scavenging approach is irreversible. Once you scavenge it, it won't come back to the atmosphere. But the other 2 approach would be, it's 2 directional. There are many unknown stuff for the gas scavenging, so I'm not going to repeat this. Apparently, a lot more need to be done on the gas scavenging. But now it's even less knowledge, so we don't have much time to repeat this. Just want to mention that this morning this paper just appeared on SCPD. We used the 43 different species of polycyclic aromatic compounds, or pH, people usually call it. Some pHs are mostly in particulate phase, some are mostly in gaseous phase. So we grouped them, and we have both snow scavenging and rain scavenging. We compared the scavenging ratio. We generated some new knowledge. For example, we found that snow scavenging is more efficient than rain scavenging for both particulate and gaseous species. And particle scavenging is faster than gas scavenging for PSC species, at least for this group of species. Okay, that's all I want to say. Thank you very much for your attention. If you have any questions.
Yes, are there any questions for Dr. Zhang? Okay. Yeah, there is a question there.
Leiming, the various models that started out with dry deposition, that's all I'll speak to here. As you noted, were very simple, using water vapor exchange, things like that.
Yep.
Have gotten increasingly complex, even to the point of now we know that different types of vegetation, even the waxy cuticular substance varies from tree to tree, and so they've tried to use fugacities and all kinds of things to really get very particular. But at what point do we try to get so realistic that we're just compounding error upon error because we're saying, okay, well, there's an uncertainty in this process, and there's an uncertainty in this number, and then we've got so many uncertainties that, yes, it's more realistic, but we actually are just adding on errors?
It's a very tough question. I think developing more sophisticated model is necessary, because if you don't try, you never know. So you try to include more processes or parameters that we think will affect the deposition process. Then we try to make as many measurements as possible to evaluate this process. Then we can simplify those sophisticated models into simple ones that's realistic, that can be used in chemical transport models. So for different chemical species, it's hard to say, how many parameters we should include. But apparently the measurement people and the modeling people should work together instead of, as separate groups. I mean, if you work together, you would know which parameter, like through numerical sensitivity test, you would know which parameter is more sensitive to the, adaptation velocity, to which parameter will contribute more to the final results. Then, the measurement people would pay more attention on that. That's all I can say. Thank you.
Anybody else? Any other question? No? Okay. If not, so I would like to thank Dr. Zhang for his participation. Thank you very much.